Hello, my name is Ana Rosas, and thank you. I am from Montclair State University. Thank you for attending my research. My research is titled Developing Equations for Two Diophantine Equations and Their Behaviors. In the introduction, I provide two equations. Equation 1 essentially represents the sum of the cubes equal to 1, while equation 2 represents the partition of 1. In this research, I deal with mod P, and essentially that just means you have a natural number that's divided by P, prime number, and you focus on the remainder. Thank you. As well, in the introduction, there are two examples. 1 plus 1 plus 1 is equal to 1 mod 2, while 1 cubed plus 3 cubed is equal to 36 mod 37. And they are in respect to equation 1 and equation 2, as shown from top to below. In the definitions, I focused on CP, which is CP and TP are both set of solutions, while alpha P and beta P are both the number of solutions for their respective type, them being type 1 and type 2 respectively. CP is essentially the non-zero perfect cubes, while TP is the total solutions. And they are shown as illustrated on the poster. In the examples, for example 1, it's the case P is congruent to 59, P is equal to 59 congruent to mod 3. Essentially, in the first row, we focus on alpha P, which is type 1. And as you can see, there are two distinct numbers. There are two common numbers, while the third one is distinct. However, the arrangement doesn't really matter because there are 3 permutations to it. So you can switch them around. In the second row, all 3 numbers are distinct, meaning you could move them, or you could move them more around, having a total of 6 permutations. In my research goals, I essentially focused on developing equations that represent type 1 and type 2, type 1 being alpha P and type 2 being beta P, as well as to continue the number of solutions in cases for P congruent to 2 mod 3 and P congruent to 1 mod 3. That will be further explained in my main results. In main results, connecting in relation to existing results, I had prior experience in relation to 1 mod 3, and this research I further expanded in the case of 2 mod 3. Essentially, in the first table shown, I focused on case 2 mod 3, where the prime numbers are as illustrated, and I developed equations in respect to P congruent 2 mod 3. So for example, for alpha P, I developed, the numbers are shown, but I developed an equation where alpha P can be explained as P minus 3. So if we have 11, for example, 11 minus 3 is 8. If we have 59, 59 minus 3 is 56. For beta P and the scalar solution, there were also equations developed, but they were more complex, as well as for TP, the total solutions. Now in theorem 2, I focused on the case of P congruent 1 mod 3, which is distinct from the other case, P congruent 2 mod 3. Essentially, for theorem 2, I focused more on solutions that involve the value 1, that being highlighted in part 3 of n1 equal to P minus 4. Essentially, if I was given a prime number, or I developed a prime number in respect to P congruent 1 mod 3, I could calculate how many solutions involved the 1 in it. So if my prime number was 13, for example, I would have 9 solutions that involved the number 1 in it. If I had 61, it would be 57. For future directions, I want to further expand on the case of P congruent 1 mod 3 because I was unable to develop an equation for beta P. as well as be more specific in the boundary of solutions for 1 Mod 3. And now I want to thank Montclair State University, as well as Professor Lee for this opportunity, and Alsam as well. Thank you, and have a good rest of your day.